Thank you, and thank you for the invitation back to talk to you once again. So this is talking about how you can take pictures of the night sky with this subtitle without using ridiculously expensive equipment. Because if you want to, you can do it the very expensive way. I'm going to tell you, if you like, about alternatives. So I'll be saying what you can do with just a camera and a tripod, what you can do if you decide to invest in a telescope and the mounts to mount a telescope. But I'll also be spending a fair bit of time talking about what you can do with a camera and a star tracker, and I'll tell you what a star tracker is in due course. And of course, I'll be showing you some of my images, and you've already seen my talk on wildlife photography, and I'll just be showing the overlap by reminding you that if you get to somewhere with very dark skies, like the middle of Africa, then you can do some astrophotography as well as photographing the wildlife. So let's start with what you can do with just a camera and a tripod if you're interested in catching not objects in daylight, but the night sky. So this is going back quite a few years now. You can tell it's quite a few years ago because at the bottom I give some details, and you can see the camera I used, a Nikon FM2, and the medium was not digital photography. We're talking about Fujichrome slide film here. So that sort of dates it to something of order 20 or so, a little more than 20 years ago. Perhaps it's more like 25 to 30 years now. So this is just a picture of the night sky taken from a nice dark sky site. This is not far from Egypt. This is actually probably inside Jordan. And I took a picture of the night sky and simply exposed for about 5 minutes or so. So this is just a camera on a tripod with a cable release, exposed for 5 minutes. And you can see that the stars have trailed. One star appears not to have moved. That's the North Star Polaris. All the other stars appear to be moving around Polaris as the Earth rotates. And you can see individual stars have moved so that you end up with small tick marks. The further away you are from the pole, the larger these tick marks appear to be. And even if I didn't tell you it was a 5-minute exposure, in principle you can work it out because you know the stars would rotate a complete circle in one day, and so by looking at how big these ticks are, you can work out how long the exposure was, about 5 minutes. If you want to expose for longer, the ticks get longer, and again, all the stars appear to rotate around Polaris. So I tried that more recently, not with a 5-minute exposure, but with a 6-hour exposure. In this case, not a single 6-hour exposure, but because I'm now talking about digital photography, with digital you have the option of not taking one long exposure, but by taking a large number of short exposures. So I took 360 exposures, each of which was 1 minute long, and then in software, you can get free software that will do this for you. You can then add all the images together to give you the same effect as a 6-hour exposure. Again, you can work out it's 6 hours because each of the stars appears to have rotated by approximately 1/4 of a revolution around the pole star. Notice the pole star is not actually absolutely at the pole. Even the pole star makes a little arc because the pole star is a little less than 1 degree away from the true pole. You can see that this particular image was taken from an observatory site. It happens to be the Canary Islands, and hence in the foreground we get a few domes of other telescopes in the foreground there. It almost looks like daylight. Here in the grass looks like it's illuminated by the sun, but no, this was moonlight. So it's the moon that's causing the domes to be bright white and the grass to be relatively green, and also why the sky is blue rather than the sky is being nice and dark. One advantage of digital photography is, as well as adding all the images together over the 6 hours, you don't have to add them all together. You can make a movie out of them if you so wish, and then add them up 1 frame at a time, and you end up with a movie of all the stars rotating around the North Pole. And again, you don't need any special equipment to do this. You just need your camera on a tripod, and preferably with the ability to take a series of images. Either the camera will have that built in a menu somewhere, or you can get little handheld intervalometers that will basically just say, take 100 pictures, each of which is 30 seconds or something like that. You can buy intervalometers for essentially any camera. So that's something you can do essentially with no additional equipment. Occasionally, something interesting happens in the sky, like a comet comes by, and again, you don't need any specialist equipment. This particular comet was so close to Earth that it was large enough that I could capture it with simply a telephoto lens, not with a telescope. This was with a 300mm lens, and it was a 30-second exposure. So in principle, the Earth has rotated in 30 seconds, and the stars might appear to have moved a little bit, but you can hardly tell, because with a 30-second exposure, the amount by which the Earth rotates isn't that much. With exposures of many minutes or hours, the movement of the stars is quite noticeable. For an exposure of a few seconds, you can probably get away with it. So this was a comet that happened to come close to us in 2005, and it was close enough and large enough that you didn't need a telescope or a pair of binoculars to see it. It was clear object, naked eye, easily caught with a camera. There are some instances where you simply have to be in the right place at the right time. With a comet, you could see that from almost anywhere on the Earth. But with an aurora borealis, you really do have to be in the right place. So in this particular case, I took a holiday up in Iceland. At the Arctic Circle, you stand a much better chance of seeing the aurora. I know they do occasionally come down to southern latitudes as far as the UK, but you're much better off going to Scandinavia or Iceland or perhaps northern Canada or Alaska to see the aurora. And it's not just a faint glow on the horizon. Once the aurora hits, it basically lights up the entire sky. The entire sky goes green, and you see these wonderful curtains. Again, this is quite a few years ago, and so I was using slide film, which has the disadvantage that you need relatively long exposures, because slide film or print film, not particularly sensitive. And so some of the rather nice detail in the auroral structures there get blurred out by the movement of these curtains of light. I would like to go back to Iceland with a digital camera being more sensitive. You can take shorter exposures, and hopefully some of that interesting detail won't get blurred out. But for quite a few hours, the sky was completely lit up with these beautiful green and red curtains of light. And in terms of being at the right place at the right time, the ultimate example of that is a solar eclipse. So again, you don't need a telescope to see a solar eclipse. This is again just a telephoto lens, my lens of choice, 300mm. Various exposures simply because the corona of the sun, which is visible when the disk of the moon covers the disk of the sun, so the main glare of the sun is removed so you can see the beautiful structure of the corona around the outside. But of course, you can only do this when you're in exactly the right place. So eclipses of the sun might happen roughly once a year, but you have to be in the right part of the world to see that. If you want to simply stay at home and wait for an eclipse to come to you, you might have to wait 100 years or so. If you're prepared to travel, then there are plenty of eclipses around in the next few years for you to go chasing. And once you've seen one, it does tend to get a little bit addictive. But again, no special equipment required. Camera on a tripod with a telephoto lens, that's it. So let's have a think about whether or not, well, let's assume you have got bucket loads of cash and are interested in doing some astrophotography. Where would you start? Well, you might say, well, I need a telescope. Okay, what telescope do you start with? Well, you start with the best telescope around. Okay, that's rather old hat now. This is over 30 years old. And because it's 30 years old, it's not going to last forever. Could appear on eBay at some point because eventually they're going to decommission it. The James Webb Space Telescope is not a replacement for the Hubble, but it is coming to the end of its life. But that's a rather expensive way of doing astronomy because the Hubble Space Telescope costs quite a few $1 billion. It gives wonderful images, and I'm sure you've seen the sort of images that the Hubble Space Telescope has produced over the last 3 decades. Absolutely phenomenal. But if your budget doesn't stretch that far, if you've got, for instance, I don't know, less than $1 billion, well, that's an option. There's a 747 with a telescope in the back there. This is an infrared telescope which is flown high in the atmosphere because the infrared gets absorbed by the atmosphere, so you try and fly as high as possible. This particular 747, it's called SOFIA, the Stratospheric Observatory for Infrared Astronomy. This was decommissioned a few months back. So again, watch eBay, because eventually this should appear because this no longer is functioning. And it only cost about 100 million or so. 747s are quite old these days, so you know they're fairly cheap. If you can't afford 100 million, well, if you have only a few million to spare, well, the Liverpool telescope, for instance, it's not based in Liverpool. It was built in Liverpool, but it's now based in the Canary Islands. And other telescopes similar to this one are available, not necessarily to buy, but you can rent them. There are various remote telescopes all over the world in very nice dark places, like on tops of mountains, etc., in which you can basically buy time. If you want to buy 1 hour on this telescope, you can buy time and take images of objects. It's not quite as satisfying as taking it yourself with your own camera and your own equipment, but if you get fed up of the UK being continually cloudy, bear in mind that you can basically buy time on remote telescopes and get some beautiful images from various places in the world, including Australia, South America, and other parts of Europe. It also has the advantage that they have their night when we have our day, therefore you can actually take pictures during the day rather than wait for nighttime. If you're an amateur astronomer and you can't afford millions or billions of dollars, I don't know why, but maybe you can't, then there are options for amateurs to say, well, I'm interested in taking pictures of the night sky, I really fancy buying a telescope. That is an absolute minefield because telescopes can be anything from a few £100 through thousands up to many tens of thousands of pounds. And the choice of which one you get, well, that is very bewildering. So if any of you are even conceiving of the idea of buying a telescope, take some advice first because it is an absolute minefield. Some people will invest in very nice looking telescopes and then insist on putting all sorts of accessories on them until you end up with spaghetti because they decide to add this, add that, add a camera, add this, add that, and you end up, for those that like technology, it's almost like the technology wins over the aim of actually trying to see something in the night sky or image something in the night sky. And some amateurs would tell you that when you're thinking of, I want to photograph something in the night sky, I need a telescope, you should not only think about the quality of the optics, you're familiar with the idea being photographers, that the quality of the lens may well dictate the quality of the image you produce, but with astrophotography and with astronomy, equally important is how stable are you going to mount the telescope to make sure that you can point at the object of interest, both in terms of making sure the whole thing doesn't wobble and you end up with an image which is jumping around all over the place, and also how accurately can you follow the stars. The Earth rotates at a particular speed. You want your telescope mount to be able to counteract that motion and follow the stars accurately to make sure that you can take nice long exposures of the night sky. So a lot of people will say you really need to invest not only in the quality of your optics, you need to invest in how sturdy the telescope mount is. And most people would say, yes, that's a good idea, but would argue as to whether or not $10,000 is a sensible price to pay for a chunk of metal whose only job is to rotate once a day so that you can follow the stars accurately. So it's a bit of an aside, but if anybody is interested in buying some optical equipment, I've got a completely different talk, which is a rough guide to buying telescopes. I'll happily send the links to that, but that's not what I'm talking about this afternoon. If you are going to buy yourself a telescope, most people would say, well, you know, putting it on a mountaintop in Chile is not really an option. I want to put it in my back garden. And when I thought about buying a telescope for myself, I thought, well, that's what I really want. I want a nice big garden with a big dome in the bottom there where I can put the telescope. I visited this site. It's Palomar Mountain in California. I visited it back in 1982. I'm not actually sure if I'm wearing the same shirt as I did back then, but that's me as a student a long, long time ago. And inside there is a telescope with a 5-meter diameter mirror. And when I looked at this observatory back in the 1980s, I thought, this is fantastic. That observatory is fantastic. When I buy a house, I'm going to make sure my back garden is big enough to have an observatory like that in the back. Okay, I had to downsize my aspirations slightly by the time I did actually buy a house and put an observatory in the back garden. It might look like a B&Q shed to you, but no, it's an observatory. It used to be a B&Q shed, but I took the roof off it, and so the roof now hinges back to show the sky. And inside there was, again, this is quite a few years old now, there was a telescope. You can tell it's an old picture not from the telescope, you can tell it's an old picture from the laptop that looks like a brick rather than a very slimline object that they are these days. So unfortunately, my back garden is getting very overgrown. There were trees that were quite small when I bought the house, and now these trees are 30 meters tall. They're outside my garden, so I can't cut them down. So that's unfortunately blocking my bit of the sky. But the idea of having a telescope in the back garden is appealing to many astronomers. And of course, that gives you wonderful views of the moon and the planets, etc. Even something, it might sound mundane, but even something like watching the shadows of the craters and the mountains on the moon change hour by hour or day by day can be quite fascinating if you can see the sort of detail that you can get with even a modest-sized telescope. But what I really want to talk about is not how you can invest thousands of pounds in telescopes to do astrophotography. I wanted to talk about how you can use cameras and so-called star trackers, other cheaper ways of getting the camera to follow the stars. If you only want to have star trails, then you can keep the camera static and the stars will move. If that's all you want, that's all you need. But if you want to be able to follow the stars, you need some way of automatically driving the camera such that it follows the stars by rotating the camera at 1 revolution a day to counteract the revolution of the Earth, the rotation of the Earth. And that's what a star tracker is. Let's just remind ourselves about cameras. You probably don't need this recap, but I'll go through it anyway. If we have a monochromatic film, effectively a black and white film, or a CCD chip in a digital camera, then when we focus light on it, well, we get a monochromatic, we get a black and white image. In astronomy, including professional astronomy, for instance, the Hubble Space Telescope works with a monochromatic camera. It doesn't have color cameras, it has a monochromatic camera. And to get color images, you put colored filters in front of the camera. Usually red, green, and blue. If you want a color image in daylight, the Hubble Space Telescope doesn't necessarily use red, green, and blue filters. It might use filters specifically to highlight particular structures in the thing it's interested in. If it's looking at a nebula and that nebula is made of certain materials like hydrogen and oxygen and sulfur, then they will use filters that specifically let through the light of those atoms that are glowing, not necessarily simply red, green, and blue. But that in principle is how all color photography was done until some bright spark realized that you could put all of those filters effectively into one emulsion, and then we had color film, color print film, and color slide film, where you had very clever layers of the emulsion with filters such that each layer gave you the red or the green or the blue elements of the image you were taking. Of course, with digital photography, it's rather different. We still have a monochrome chip. We still have a black and white chip that's recording the light, but on top of the chip are the colored red, green, blue filters. If we were to look in detail at a CCD chip and blow it up, we would see that the individual pixels have red, green, blue filters in a particular pattern. Most patterns look like this. It's a so-called Bayer grid. Different manufacturers will make the Bayer grid in slightly different ways, but essentially most manufacturers will end up obtaining the red and the green and the blue parts of an image by arranging them in this sort of checkerboard fashion. So when we think about what the camera is actually recording, it's recording red and green and blue pixels in this particular pattern. So clearly it's a relatively sparse pattern. We have to interpolate to work out what the intervening pixels are. You also notice there's twice as many green pixels as there are red and blue. That's quite handy because human vision is very sensitive in the green, less sensitive in the red and the blue. So when you're taking a picture in daylight, it's not a bad idea to get as much information as you can in the green channel, because that's, in a sense, mimicking how human vision works to an extent. When it comes to astrophotography, you could say, well, I want the best possible image. I love these pictures that the Hubble Space Telescope is producing. I want to buy myself an astronomical camera, a camera dedicated to astrophotography, so that I can emulate the Hubble and all these other wonderful images that I've seen in magazines and on the interweb, etc. And indeed, there are plenty of cameras that you can choose from. For instance, at the lower end of the market, you could spend £100 or £200 on a relatively simple camera, a camera that will effectively replace the eyepiece in a telescope, and a color camera you can buy for maybe a couple of £100 or so. If you want a high-resolution color camera, you can spend almost anything you like. Again, £1,000 or £2,000 or £3,000 is not that unusual. If you want to, you can spend £5,000 on a high-resolution color camera. What is perhaps surprising is that if you wanted a high-resolution mono camera, it's actually the same price. The manufacturer, in terms of how much does it cost to make these cameras, it doesn't actually add any cost to add that Bayer filter to the front element of the CCD, or at least it adds so little. A lot of manufacturers will effectively give you the same price for the mono version of a camera or for the color version of a camera. So in this particular case, similar resolution, but similar prices. If you wanted to take color images with a mono camera, then you would have filters in front, and it is not unusual to have filters in a wheel where the wheel rotates under computer control to give you one filter, you take a picture, then it rotates to give you another filter, then you take a picture, then it rotates to give you a third filter, then you take a picture, and then software afterwards recombines those images into a color image. But that costs as well. So you can see that unless you're going for the very simplest low-resolution camera, as soon as you talk about cameras that are dedicated to astrophotography, things start getting very expensive. And that, of course, is on top of whatever price you decide to pay for a telescope or a mount or anything else. But the main point I want to make in this particular presentation is, because I'm talking to a photographic society, you probably already have a camera. It might be a DSLR, it might be a mirrorless camera, it might be a bridge camera, it might even be a compact camera. But if you've already got a camera, why would you consider investing in an astronomically dedicated camera if you've already got a perfectly good camera available to you? And that is, in essence, the situation I found myself in. I had a camera anyway because I was interested in, for instance, taking pictures of wildlife. And I thought, well, if I've already got a camera, can that same camera be useful for astrophotography? It's not designed for astrophotography, it's designed to take pictures in daylight. It's designed to take pictures when there's a lot of light available. But will it also work if there isn't much light available? That's why I'm talking about star trackers. If we want to use our own camera and take pictures of the night sky, we need some way of tracking the sky in order to follow the stars. And some years ago, not quite 10 years ago, 2007 or so, I decided to build myself a star tracker. Given that a star tracker is just a mechanical or an electronic device that rotates at 1 revolution per day, I thought it ought to be possible to build one. So I built one for myself. They cost about 10 or 20 or 30 pounds, depending on what bits and pieces you happen to have lying around in your garage. And if anybody's interested in building one, I have the instructions how you can do that here, if anybody wants to take one of those away. So you can build yourself a star tracker, and it's basically just a couple of hinges and a motor at this end, and the motor simply makes the top half rotate relative to the bottom half at the rate of 1 revolution per day. If you don't fancy building one for yourself, you can just go out and buy a star tracker. They cost anything from £100 or £200 or thereabouts, so it's much cheaper to build your own, much more fun to build your own. But if you don't want to, you can buy yourself a star tracker for much less than it would cost you to buy a telescope and a mount and everything else you need for astrophotography. So, although I built one for myself, I did try this commercial device here. It's made by a company called Dioptron. Other star trackers are available. There's at least half a dozen different companies who make different versions of star trackers. And this is one I've been using since about 2015 or so. This is how it works. Basically, it's a box, and you put that box in between your camera and your tripod. So it's relatively simple to set up. You make sure your tripod is nice and steady. You put the box on top, and then the camera, quite often with a ball and socket joint, doesn't have to be. You can mount it in pretty much any way you like, but ball and socket joints are quite popular ways of mounting the camera onto this, such that the camera can point to effectively any part of the sky. The little small telescope on the side there is designed to line up with the Earth's axis. because if the Earth is turning at a particular rate, you want to not only turn your motor in the opposite sense at the same rate, you want to make sure that your two axes are lined up. So if Earth is spinning this way, you want to make sure your motor is spinning the opposite way on the same axis. So we want to be able to line up the North Pole. Polaris is very close to the North Pole, so from England it's very easy to just tilt this over because it has a little tilting mechanism at the bottom here. Tilt it over until you can get Polaris lined up in this little telescope. That tells you you're parallel with the Earth's axis, and the internal motors then guarantee that the camera is turned at the right rate to follow the stars. So the inside of these things is not particularly complicated. They are reasonably robust, reasonably rigid. It works well for small cameras. I've tried it with my camera and a telephoto lens. I'm not sure how many kilos that is. That's got to be more than a kilo, less than 2 kilos of load on top of the star tracker. That's not really a problem. So 300 millimeter lens is about the limit of what I would try to do on one of these star trackers. And smaller focal lengths down to wide angle, perfectly okay. This is just for context. What's inside the white box? Well, some AA batteries, some electronics, a motor, a gearbox, and then the final drive is this worm and wheel. Because of course, one rotation per day is relatively slow, so the motor is turning fast, but it's geared down by thousands to one, such that in the end, this wheel here, this gear, turns at just the right rate to turn to compensate for the rotation of the Earth. Strictly speaking, it's not one rotation in 24 hours. It's one rotation in 23 hours, 56 minutes, because that's how long it takes the Earth to turn once on its axis. You tend to think of it as 24 hours, but that's how long it takes to turn relative to the sun. And remember, the Earth is going around the sun. The length of time it takes the Earth to rotate relative to the stars is once in 23 hours, 56 minutes. And that's built into the electronics of these devices to make sure that the motor turns at just the right rate to give you that speed of rotation. So as long as you set it up correctly, you should be able to follow the stars, and the stars should not trail into little streaks, but should stay pin sharp. So let me show you some images that you can obtain with a camera that's not designed for astrophotography, just an ordinary camera, not modified in any way, and what happens if you point it at the sky. So most of what I'm going to show you, I tend to be a little bit of a Nikon guy. I bought a Nikon D70 many years ago. I'm now using a Nikon D7500. It really doesn't matter what type of camera you've got, whether it's a Nikon, whether it's a Canon, whether it's a Sony, whether it's a Panasonic. It makes little difference. It only makes a subtle difference in the sort of images that you produce. And a reminder that these are images of the night sky not involving the use of a telescope. This is just a camera with whatever lens I happen to have. Either a wide-angle lens if I wanted a large chunk of sky, or a telephoto lens if I wanted a little bit of detail. Exactly the same lenses that I might use, for instance, if I was trying to take a picture of a lion or a zebra or a giraffe on safari in Africa. So you can take pictures of nebulae and galaxies and stars that have blown themselves to pieces and our own Milky Way galaxy quite happily with a star tracker. So absolutely, astrophotography using a telescope, enormously rewarding. If you buy yourself a telescope and take images through a telescope, that can be fantastic. And that's quite often what you see when you look at images in various magazines and on the internet. But to get the most out of astrophotography with a telescope, it will take time, it will take effort, and it will take cash. And everybody seems to underestimate all of those three factors. You can't simply buy yourself a telescope and hope to be imaging a remote galaxy the following night. It will take you time to build up the skills to use the telescope and do the astrophotography. It will require time and effort, and you will have to invest thousands of pounds to do it properly, which is why I'm telling you, you don't have to go that route. You can take the camera you've got, build yourself a star tracker for 20 quid, and then obtain some interesting images. One thing to bear in mind is if you're not going to a dark sky site, if you take images from suburbia, there will be light pollution. I happen to live in an area where there's lots of street lights around. I'm on the edge of a town. There's plenty of street lights. It's well lit, and therefore there will always be some light pollution. You don't always notice it. When you look on a nice dark night, it might look like the sky is quite dark. But when you take an image, especially when you take a long exposure image, you may be surprised to find the sky comes out a lot more orange than you appreciate. That's simply because your night vision is not good enough to show you the glow in the sky. But as soon as you try to take a long exposure because you're interested in some of these faint objects that are out there, the light pollution may become evident. Such as the image on the left-hand side, that might be what you get on the back of the camera. That might be what the raw image looks like as soon as it comes off from taking, I don't know, maybe a 60-second image of a particular chunk of sky. That might be what you see. But the good news is software is fantastic at dealing with that. Because sky pollution effectively covers the entire image, it is possible to compensate for a certain amount of light pollution. Unless it's really, really bad, you can do a good job by simply asking pieces of software, some of which are free, some of which you pay for, it's your choice. Software is generally very good at taking an image that starts out looking like the left-hand side and ends up looking like the right-hand side. They are the same image, but simply processed in such a way that the orange glow in the background is suppressed to make it not black, but at least dark. And then you bring out the colors of this nebula, which you can probably see just about lurking on the left-hand side there. You can see why this particular nebula is called the North America Nebula, yep, because of the outline that you can see there. This particular nebula, this particular cloud of hydrogen and oxygen seems to be glowing slightly pink and slightly blue. That's not artificial colors. It's not false colors. What I'm dealing with is a camera that's designed to work in daylight, and wherever possible, I try and process the images such that the colors are preserved. The sort of images that you might see coming out from the Hubble Space Telescope, they might be false color in the sense that that is not the colors of the object that you would see if you were standing in front of them. They've been processed in such a way as to bring out some of the detail by applying false colors in order to exaggerate certain features. Wherever possible, I try and make sure that the colors are as close to what I believe is natural colors. And you can tell what's natural colors because, for instance, certain atoms emit certain colors. We know that hydrogen emits a red color. We know that oxygen atoms in the nebula will emit a blue color. So we know what sort of colors they're supposed to be, and therefore we can always try and make sure our color calibration is approximately correct. So here's an image, again, taken with my current camera. So this was taken a few months ago with a 300mm lens. This is a particular nebula, a cloud of hydrogen in space, which is a sort of stellar nursery, if you like. For those of you familiar with the constellation of Orion that you see in the winter sky, this is just a little bit left of the constellation of Orion. Again, it's glowing mainly pink, because this particular nebula is made of hydrogen, and this hydrogen is the source in which these particular stars are being born. So this is a nursery in the sense that this is how stars are born. They start as a large cloud of hydrogen, the hydrogen cloud collapses, and then stars are born in the center. Again, I point out the fact that this is not one very long exposure. It's not a particularly bright nebula. You can't simply expose for 10 seconds and hope to see a lot of detail. This particular exposure was about an hour, but you don't expose for one exposure in an hour. You take a lot of short exposures. For instance, I might take a very large number of 30-second exposures and then add them all up together in software afterwards. This has a number of advantages. For instance, you take maybe 100 images, each of 30 seconds. If one of them is spoilt by an aircraft flying through your field of view, fine, you throw that one away and add up all the other ones. If clouds come over during the hour, okay, you just ignore that and keep all the rest. If you had one long exposure and it gets ruined by an aircraft flying through, there's nothing much you can do about it. But if you have lots of short exposures, you can decide which are you going to keep and which are you going to throw away. This is it looks perhaps a rather lower quality image. This was taken quite some time ago. The Nikon D70 is one of the first digital cameras I bought. Again, this is probably now getting on for 20 years old, I guess. So it doesn't look particularly good necessarily, but I thought this was quite interesting. It's showing a star in the middle there. This is a star that's come to the end of its days, and as stars get old, they tend to puff off and slough off, shrug off their outer layers. The outer atmosphere of this star has been blown off into interstellar space, leaving a small star at the center. And so this blue and white and pinky region is a nebula formed from this star expanding and producing this nebula. I show this because an interesting comparison is, if that's what you can take with a camera that's designed for daylight photography, how much better can you do if you have about $10 billion? And that's the Hubble Space Telescope picture of the same nebula. Now, I admit the Hubble is better. Yes, okay, definitely the Hubble image is better than my image. But this image, given that I already had a camera and already had a tripod, this image cost me about 20 quid. The Hubble Space Telescope cost somewhere in the region of 10 billion, and I don't know how many years of effort. So the colors aren't quite right, and there's definitely more detail in the Hubble. But if you look at Hubble pictures and think, that looks fantastic, I'll never be able to take pictures like that, wrong. You can take images that are lower resolution, not as good, a little bit more scrappy, but the enormous satisfaction of taking them yourself rather than taking them from an international project like Hubble. This was taken a few years ago, pre-COVID. This is a star, not a star being born out of a cloud of hydrogen. This is the death throes of a star. There's a star embedded in that rather bright white region there. The star is called Eta Carina. It's one of these stars in the constellation of Carina, which is visible in the southern hemisphere. So this was taken when I was on safari. It wasn't taken from the United Kingdom. It was taken when I was on safari in Kenya. And this is a patch of sky that can't be seen from England, unfortunately. But this particular star is extremely unstable, and people have been watching this star for quite a few years. It looks like this star, again, is expanding and contracting, and a lot of material is being lost from this star. It's been speculated that this star is coming to the end of its life and may, before too long, end its life in a supernova explosion. It's very difficult to tell if there's going to be a catastrophic end to this star. It will happen. It's very difficult to tell when it will happen. But in this case, not a 300mm lens. Notice that this is quite a large object, so this was taken with an 85mm lens, just a portrait lens. It gives you an idea of just how large these objects are in the sky in terms of their angular size. The fact that a portrait lens can get you this cloud of hydrogen tells you that these aren't tiny things. Yes, they are very remote, but they are close enough that they subtend a substantial angle in the sky. So you don't need very large telescopes to see them. Even modest lenses might be enough to capture detail in these objects. This is one that quite definitely has gone bang. This is one that blew up about 10,000 years ago. So somewhere in the middle there, who knows which, there was a star that went supernova and blew itself to pieces. And what you see here is a sort of bubble produced by all of that material expanding for the last 10, 15,000 years or so. So it's probably a spherical bubble, but have you ever noticed that when you look at a soap bubble, you tend to be able to see the edges, but you can't necessarily see the rest of the sphere. You tend to pick up just edges, and that's what we think is going on here. It's probably a complete sphere of material, but it's very difficult to see the material in some regions, and when we're seeing this sphere edge on, as it were, we see a lot more of the material, and it looks a lot brighter. Again, the colors, I believe, are real. This particular thing, it's been shown by other people studying it. This particular shock wave produced by this bubble expanding in space is made of hydrogen and oxygen. Hydrogen should glow red, oxygen should glow a sort of bluey green, a sort of cyan color. So this is close to the genuine colors. This isn't as bright as it appears in the sky, Remember, your night vision is not very good at picking up color, so if you were to look at this object through a telescope, you might see this structure, but you wouldn't see these colors, because human vision does not work very well at low light levels. But as far as I can tell, those are genuine colors. Again, this is being picked up by her 300mm lens. Just to give you a sort of scale, this object, if you think of this object as a bubble, this object is larger in the sky than the full moon. That gives you an idea of just how big it appears to be. The full moon is about 1/2 a degree in size in the sky. This object is bigger than a degree. It is quite a few full moons from one side to the other. In this particular case, this is one of the few times when I've actually used a filter. I usually don't use filters. You don't need filters if you've got a nice dark sky sight. But this was taken from outside my front door. And outside my front door, I have street lights. And street lights were streaming into the camera and lighting up the sky. If I didn't use a filter, I would have found it difficult because the sky was so bright, it would have been difficult to see the nebula against the bright sky, even with a little bit of image processing. So in this particular case, I've used a filter which reduces the amount of light from the street lights, but lets through all of the light from the supernova explosion, because the supernova is hydrogen and oxygen emitting light at particular colors. If you let through those colors and reject everything else, you still get the nebula just as bright as it would be, but it suppresses the light from the street lights. So it would have been tricky for me to take this from my particular location outside my front door without using a filter. Most of the other pictures I'm showing you do not use filters. We can go beyond looking at supernova explosions in our own galaxy. This is a nice region of the sky a little bit further south in terms of a little low on the horizon as seen from the UK, a little bit higher in the sky as seen from other parts of Europe or parts of Africa. And this is a particular chunk of sky. One thing you notice is the sky is full of stars. It is not a problem picking up stars. Stars may appear faint, and you may think that a camera designed for daylight might have trouble picking up starlight. But in fact, whenever you point it at the sky and take a long exposure, the problem is you get so many stars that sometimes it can be difficult to see other objects of interest in the sky. So this happens to be a part of the sky which is absolutely dominated by very crowded star fields, but I took this picture because I was interested to try and bring out the colors of these nebulae here. Here's a cloud that's being illuminated by this star, which is tending to illuminate it and makes it look a little bit orangey yellow. There's another star over here, which is a relatively blue star, and that is lighting up this part of the nebula, and that's producing a bit of a blue glow. Notice there's other rather dark regions where light appears to be absorbed. If you're very eagle-eyed, you might also notice there's a huge star cluster here. This is hundreds of thousands of stars in a relatively small region of space, a so-called globular cluster. So let me just label some of these. There's a very large star called Antares. That's a star cluster called Messier 4. That's the name of that particular star, lighting up this nebula in giving this lovely blue color. And in this region, there's lots of other clouds which are not being illuminated by stars, and hence these clouds appear to be dark. Generally speaking, clouds will appear to be dark unless they are being illuminated by stars that are embedded in those nebula, in which case you get the beautiful colors. And this is just a nice contrast between different colors and different dark nebulae as well. And again, we think that there's all sorts of molecules in these structures. There's hydrogen, there's oxygen, there's water, there's probably loads of other molecules buried in these clouds out in the cosmos. But we can move beyond our own galaxy and say, well, can we actually take images of other galaxies? So this is the Andromeda galaxy. This is one of our nearest neighbors. Again, galaxies tend to be far, far away, as you know from Star Wars. And you might think that in order to take a picture of a distant galaxy, you need a telescope with a high magnification. No, absolutely not. This happens to be our nearest neighbor, and in terms of how big does this galaxy appear to be in the night sky, it is much bigger than the full moon. Again, if I were to take a picture of the full moon might be about that big, something like that. In other words, next time you see the moon, just mentally add on another 2, 3, 4, 5 moons. That is the sort of the size of the galaxy that we're looking at here. Again, when you look at it with your own eyes, you can see it with the naked eye, but your night vision of humans, because we're not nocturnal basically, is not very good. And because night vision of humans is not good, we don't see the galaxy looking like that. We see the brightest part of the galaxy, but we don't see the faintest the faintest edges. Only by taking images do we see the light from the edges of this galaxy and appreciate the entire structure of this huge rotating star city. In fact, not only can we see the galaxy itself, the Andromeda galaxy, we notice that it has 2 little satellite galaxies. There are 2 small galaxies that are buzzing around the Andromeda galaxy in much the same way that small galaxies are in orbit around the Milky Way as well. But it is, I think, rather remarkable that you can see this level of detail in a galaxy that is 2 million light years away. So the light from this object has taken 2 million years to reach us, about 2.5 million years. And a camera that's designed to work in daylight can still produce images like that. Cameras that are designed to work with lots of light tend to produce a little bit of noise when you're trying to look at very faint objects. But the noise levels of modern cameras compared to 20, 30 years ago is so good that you can take images like this. Again, in this particular case, what's this? 30 minutes exposure. 30 exposures, each of which was 1 minute. Add them all together, and you can get images like that sitting on a star tracker. But that's not the limit in the terms of how far out can you go. I was quite curious, especially during lockdown, and asked myself, well, I can certainly take pictures of a galaxy 2 million light years away, so the light has been traveling for 2 million years. But what's the most distant object that I can possibly pick up with my Nikon by putting it on a star tracker and then taking a long exposure? So in 2020, I set myself a lockdown challenge because we weren't allowed to go out and socialize. So I thought, right, what I'll do is I'll plan on taking a photograph of an object and see if I can get a really, really, really distant object and pick it up with my camera. So I set myself the challenge. I got my trusty star tracker out. I put my 300mm lens, my lens of choice, on the star tracker, and I pointed it at a chunk of sky where I expected to be a very distant galaxy. How did I know? Because I went and looked it up. I found a research paper that said, here's a catalogue, here's a list, if you like, of lots of distant galaxies. These are the bright ones, these are the distant ones, these are the ones you can see from the UK, etc. And I figured out in the summertime in the UK, what is nice and high in the sky. We don't want something skirting the horizon where it's all murky. We want something nice and high in the sky. I want it to be visible in July when I took these images. And I want it to be bright enough even though it's at an incredible distance. So I found a target. It's not that thing in the middle. That just happens to be a star in our own galaxy. But in terms of line of sight, it just happened to be next door to that star. So I thought that's handy, because if I can get that star, then I know the galaxy that I'm after is right next to it. The galaxy that I'm trying to image here is called a quasar. A quasar is just a name for a galaxy that's emitting a huge amount of energy. So even though it's very remote, I stood a chance of catching it. So I took a long exposure, about 2 hours. 2 hours was the maximum I could do because, as you probably know, in July in the UK, you don't get much night. You get dusk, and then it seems to be dawn almost immediately. You get perhaps 2 hours where it's relatively dark, and those are the 2 hours that I imaged this particular object. I expected the galaxy that I'm after to be inside the middle of that yellow square. So I took my whole image and then zoomed in, hoping to pick up this distant object. And it is the least spectacular image I'm going to show this evening, but that is it. That is the galaxy that I was trying to image. Most of the light from this particular galaxy, this particular quasar, is focused into, roughly speaking, 1 pixel in the image. It's a 20 megapixel camera but all of the interesting action goes on in 1 pixel. I can blow it up and that's it. I've exaggerated the contrast of the neighboring pixels just so you can see it most clearly, but most of the light from that distant galaxy has gone into 1 pixel and perhaps a little bit into the neighboring pixels. The most incredible thing about this image is the fact that it exists at all. Because what you can ask yourself is, well, where did that light come from? How long has that light been traveling to reach us? Remember the Andromeda galaxy, it had been traveling for some 2 or 2.5 million years. This object is at the incredible distance, the mind-boggling distance of 25 billion light years. And the light has been traveling for that length of time. The light has been traveling for 12.4 billion years. Remember, the Earth is only 4.5 billion years old. So the light that produced that little white blob there, that light left this distant galaxy very early on, not long after the Big Bang, and it was traveling for billions of years, even before the sun existed, even before the Earth existed, way before the dinosaurs existed. It's been traveling for 90% of the age of the universe. So it was born when the universe, it was emitted when the universe was a baby, and it's been running ever since. The universe is expanding. So not only is this a very distant object, when we think about the universe expanding, all of these distant galaxies are being carried away from us. This particular object, I calculated, is moving away from us at approximately twice the speed of light, which is pretty amazing to think of the universe expanding such that an object is moving away from us at twice the speed of light, and yet it is still possible for the light eventually to make its way to us. That is an absolute mind-boggling thing. I wasn't expecting to find that. I was hoping to see the object itself. I wasn't expecting, when I calculated it, to find that it's actually receding from us so fast. But there are lots of objects in the universe that are moving away from us at that speed. When you look at Hubble pictures of distant galaxies, some of those will be moving away from us at greater than the speed of light. The fact that you can still image, it's really not an easy thing to get your head round. I had to sit and think about this over quite a few cups of tea until I was happy with the idea that an object moving away from us at more than the speed of light can emit light which can still eventually reach us. It is by no means intuitive. It is completely counterintuitive, and I was most pleased for this lockdown challenge to find that I could get a little white square. It might only be 1 pixel in the image, but when you think of the journey that the light has had in order to make that little white pixel, it is truly mind-boggling that a camera designed for daylight photography and taking pictures of your kids or the dog or flowers can take a picture of a galaxy on the other side of the observable universe. The fact that technology allows you to do that is incredible.
Sorry, but could I ask a question?
Yes?
While we're on that, I find that quite mind.
Absolutely it is, and which is why I'm skipping over it, because I do not have... Yeah, well, either...
Well, the question is, I thought we couldn't travel faster than the speed of light.
The universe can expand at any speed it wants to. You cannot move through the universe. You cannot move through space faster than the speed of light. But the universe can expand faster than that. It has done in the past, and it is doing now.
So the universe can expand faster than the speed of light?
It is doing, yes.
I find that.
Yes. A, it's incredible. B, I have a piece of paper about that. C, I can send you a link. Or D, I've got another talk on that. Are you okay if we just spend 5 minutes finishing and then return to that? It is so mind-boggling. You can't give a superficial answer that keeps people happy. Yeah. Yeah, and I'd be disappointed if somebody didn't. Yes.
Essentially, it's switched off. It's out there, apparently travelling at twice the speed of light. It's switched off. We'll never see those.
I've got those photos.
They were emitted so long ago when it was...
Oh, sorry, photons emitted now.
Yes.
Correct. Photons emitted now will not reach us. Yep, yep. So we are, of course, looking back in time. That's what always happens. When you look at the moon, you're looking at the moon 1 second ago. When you're looking at Andromeda Galaxy, you're looking at that 2 million years ago. That is a 12 billion year old image in that sense.
If we in 12 billion years with our camera to take a picture of that, we would never see it.
Correct. Yes. So I said I would give a little bit of a heads up in the sense of if we want a tea break in the next 5 or 10 minutes, let me just give you an idea of what can be done. You've already heard part of this because wild astronomy is really combining wildlife photography with astrophotography, because if you're interested in wildlife, you probably will have a pair of binoculars on you. If you're interested in astronomy, you might have a pair of binoculars on you. If you're interested in photography, you might try photography of wildlife, and I'm just telling you now, you can try photography of distant objects. So all of these three interests of mine overlap, and that little middle section is safaris. If you go on safari, you can go to Africa, you can take pictures of, you can see animals, you can take pictures of animals, and you are away from light pollution, which means you get beautiful images of dark skies. So basically, you can take pictures of animals by day, stars by night, and you just sleep when you get home. So I've got a safari booked for August. So I'm going back to Kenya now that COVID is out of the way. We can re-establish the idea of going to these wonderful places in the world. So I've taken the sky tracker with me. It's easy to use in England because all you need to do is to line this up on Polaris, and an app will tell you where Polaris ought to be in terms of how it moves around the North Pole. But we have a catch. If we're going to Africa, the North Pole is, of course, directly above the Earth's North Pole, and we are in England at a latitude of 50-something degrees, and so we can easily see the North Pole. But if you're on the equator, like Kenya is, well, that means North Pole is on one horizon and the South Pole is on the other horizon. In principle, you can't see either of them, especially if they're behind an elephant or hills or something else. So there is a technical problem with using a tracker on the equator. But it is still possible with a little bit of jiggery-pokery and a bit of ingenuity. It's easy to do in the UK. You have to think a little bit about how you're going to set up your tracker if you're on the equator. But it is possible. There's a picture of one of our satellite galaxies. I mentioned that Andromeda Galaxy has got a couple of satellites going around it. That's one of our satellites. It's called a Large Magellanic Cloud. We have 2 big satellites orbiting the Milky Way, lots of small ones, a couple of really big ones. That's the largest one. So that's, in effect, a galaxy in its own right. It's just a relatively small one compared to the Milky Way galaxy. Oops. In terms of seeing the Milky Way itself, of course, you can see the Milky Way from the United Kingdom, but it tends to be a little bit difficult to see, partly because the amount of water vapor that tends to be in the UK atmosphere, and partly due to light pollution. So that is my estimate of what you might see if you were looking at the Milky Way in England, whereas what you would see of the Milky Way in Kenya, away from light pollution, looks more like that. You see much more structure, you see the bright regions, you see the dark dust lanes, you see a lot of structure within the Milky Way. All of the stars, all of the hundreds of billions of stars that are strewn across the Milky Way that we are seeing from the inside of the galaxy. You can perhaps tell from this particular image that this is a mosaic taken with, in this case, a wide-angle lens rather than a telephoto lens. But the usual idea of take a few short-ish exposures, in this case 2-minute exposures, I took 10 of them in 2 particular panes and then made a mosaic. But of course the advantage is not only can you see more detail when you look at the Milky Way from a dark sky site, with photography you can start to pick up the color as well, and you realize that the sky is not just black and white, the sky is quite definitely colored. Just for comparison, I went back and looked at an image I took a long time ago using slide film, ISO 200 slide film. This is the constellation of Scorpius, for those that know your way around the night sky. It's one of the few constellations that actually looks a little bit like the animal it's supposed to represent. So you can see the stars of Scorpius, but you can see very little of the Milky Way, simply because slide film is not particularly sensitive, especially at very low light levels. In this picture in the background, There are so many stars, it's actually difficult to see constellations because the bright stars don't show up compared to all of these millions and millions and millions of fainter stars. So the constellation of Scorpion is there on the right-hand side. Let me just highlight it for you. There's the constellation of the Scorpion, just like we saw here, and you can just about see the Milky Way here, but nothing like you can get with the image in the background there. And that's simply the difference between slide film and digital photography, and the fact that I took a much longer exposure. Let's be fair, it was a longer exposure for this image in the background than it was for this image here on the slide film. Slide film, of course, doesn't record how long the exposure was. That's the beauty of digital photography. It tells you what the aperture was, what the exposure was, etc. I cannot remember offhand how long that exposure was. The stars haven't moved much, and this was before I had a tracker, so I would guess this is a 30-second or a 60-second exposure. If we come back to this image, just blow it up slightly, the very bright object there is not a bright star in the Milky Way. That happens to be the planet Jupiter that was going past at the time. Over on the left-hand side, we have the planet Saturn. Everything else is either a star or a star cluster. That's a bright star called Antares. That's the one I photographed and showed you a little while ago. And when you look at images like this, you find that there are dozens, if not hundreds, of star clusters and clouds, nebulae, scattered all over your images. It's almost impossible not to take an image, a wide-angle image, and then look at it and compare it with either an app or a star atlas, and then say, look, I've got that nebula. Oh, I got that star cluster as well. All of these star clusters have already been catalogued by people, including way back to the 18th century. So, for instance, the astronomer Charles Messier catalogued a lot of these interesting objects back in the 18th century. He wasn't interested in star clusters and nebulae. He was interested in comets. So he said, that's not a comet, that's not a comet, that's not a comet, and he basically listed all the things that aren't comets so that he wouldn't get fooled next time he looked at that part of the sky. But the catalogue that he ended up with, the Messier catalogue, ends up as a useful way of identifying all of these various interesting objects. This is the one, I'm not going to zoom into that because I won't show that much detail, but if you were to zoom in a few thousand times into that particular nebula, that's the one that contains the pillars of creation that the Hubble Space Telescope concentrated on when it was first put into use. Notice that all of these things seem to stop, and only the top half has lots of interesting star clusters and nebulae. Does that mean the galaxy doesn't have anything interesting going on further south? No, that just means Charles Messier was a Frenchman, and that's as far south as he could see from France. He couldn't see anything further south than that. Back in Kenya, we have a much better view of the sky because we're on the equator, so we can see much further south than you can see from France or the UK. So, before I actually finish, let me just say I did try, as well as taking wide angle, I just did say to myself, I wonder if you can just zoom in and see a bit more detail in these regions. Wide angle lens is not really the best way of looking at detail. So I said to myself, right, let's just do another switcheroo. I normally use the 300mm lens for animals. I've been using the wide angle lens here for these pictures of the Milky Way. What if I switch to the safari lens, the lens I use for animals, and take a more detailed view of this set of nebulae, these pair of nebulae inside the red rectangle there. There happen to be two nebula. One's called the Lagoon, one's called the Trifid Nebula. And this was a single 30-second exposure. This is not dozens of different images all added together. This is not many minutes exposure. It is a single 30-second exposure. I was limited simply because of, at that time of night, the wind was getting up and I decided to pack away. But before I packed away, I thought I would take one last image. So a single 30-second exposure shows structure within those two nebula. And if I take that and simply blow it up a little bit so you can see it, you actually get some rather nice colors. The stars are starting to look a little bit bloated because this is quite an expansion of the original image, but you can see that one star is illuminating part of the nebula a sort of pink color, and a different star is illuminating and giving you a few blues. So you get the colors coming out even in a situation like this when you have a relatively short exposure of 30 seconds. For most astrophotography, you try and expose for as long as you can, many minutes. If you've got hours, you expose for hours. The fact that you can get something quite nice in only 30 seconds, I thought was quite interesting. So the takeaway message is, if you're going anywhere in the world, or indeed anywhere in the UK, in which you're likely to get away from a little bit of light pollution, you can deal with light pollution with filters, but if you get away from light pollution, so much the better. If you're going anywhere on holiday where you're likely to be under dark skies and you're taking your camera with you anyway, why not think about a star tracker? Because then you'll be able to get some superb images of the night sky without using horrendously expensive equipment.
I take it a star tracker is no good trying to get pictures of the Mars and Venus and all that.
You really need magnification. For images of very small objects like planets, you need magnification. So it's not the tracker, it's the fact that a wide-angle lens won't give you the detail, a telephoto lens won't give you the detail. You need a focal length, ideally, of 10 meters or so to get a good view of a planet. So, thank you.